right. Today we have our third speaker of the term, Jing Yu, who is a new faculty here at the University of Washington over in the Electrical and Computer Engineering Department. She comes to us after recently obtaining her PhD at Caltech and doing a postdoc over at the University of Illinois, Urbana-Champaign, and the University of Michigan. Is that right?
Yes.
And today, she'll be talking to us about set-based adversarial online control of unknown systems. So with that, I'll go ahead and hand it over to you.
Thank you for the nice introduction. It works. Okay, so in the past decade, the US has been accelerating its transition towards sustainable energy. And a lot of these changes are actually happening in our day-to-day life. So more and more homes are building solar panels and constructing battery storages. And the power grid itself is going through some major paradigm shift. And unfortunately, in this process, you probably have experienced more outages than usual. And finally, on the demand side, more EVs are on the road than ever. And if you're like me, who got a little bit too comfortable with AI tools in my day-to-day life, you would hope that this entire, energy pipeline that is going through these transitions are going to still work reliably and stably, and hopefully as reliable and stable as the traditional fossil fuel-based energy, hopefully more. So to do this, there's a whole long list of technical challenges that we must address before we can get to 100% renewable energy systems. And one of the most important challenges among them is uncertainty. So we must be able to deal with uncertainties all throughout this entire pipeline. So for example, it is well known that renewable energy generation is very hard to predict because it's volatile. So take as an example of the wind and solar energy generation during a typical 2-day period from the Arizona Public Service systems. Here you'll see that despite historical data, the prediction and the actual generation actually have a huge discrepancy. And the power grid itself is dynamically changing all the time, and it has a lot of switches during hour to hour, and these switches are only going to happen more often due to the renewable energy supply. And so take as an example the distribution power grid, and this is the part of the power grid that connects directly to our homes and schools. And due to a variety of reasons that we already know, sometimes even the temperature fluctuation throughout the day, the line impedance actually changes quite a bit. And this might be surprising, but the grid operators themselves do not usually have exact grid topology information in real time. And finally, the demand is growing with increasingly large and rapid changes because of the emergent technologies like EV charging and data centers that are powering a lot of the AI tools that we use. So the data centers alone are going to account for as much as 12% of the entire US energy electricity consumption by 2028. And this just means that a big portion of our energy consumption behavior is driven by these data centers, but data centers aren't humans. They don't have a 9-to-5 job. They don't have predictive behavior, in the nighttime where they will wind down and go to sleep at midnight. They run 24/7. And if there's a job going on somewhere in the world, it may just be transitioned in a particular data center, and there's a high demand all of a sudden. And so all of these uncertainties are creating a lot of challenges for us to design algorithms for power grid. And so if we're talking about controlling a system, and a lot of these systems can be modeled as dynamical system, and we want to deal with uncertainties, it's natural to think about control theory. That is exactly what control theories are designed to do. But in its most traditional form, control theory usually requires accurate models, and it can only handle up to some small uncertainties. Now, to address this challenge, there's a significant interest in the recent years to combine control theory with learning-based methods. That's why we're here. This is what the seminar is about. And there are a lot of cool results coming out, and now we can find ways to deal with larger uncertainties and even entirely unknown models. But I want to argue that there's still a lot of unique challenges that present themselves in the sustainable energy system domain. So for example, for a lot of these systems, learning actually have to happen on the fly and from scratch. So you don't have time to wait around, collect a lot of data, retrain or transfer your reinforcement learning policies, and then say, I have guarantees, all right? So if the topology is changing as a grid operator and I see some bad behavior, I only have a short window of time doing this transient behavior to ensure safety. And these systems sometimes are large scale and they have additional network constraints that come with it. And so the controlling of them and also data collection part of the operation has additional challenges because of these network constraints. And finally, of course, they are safety critical. So as much as we can, we want to give theoretical and empirical guarantees for these systems to operate in a safe way. And so to address these challenges, I'm going to introduce a data-driven uncertainty set-based online control framework in this talk. And the idea is very simple. We're going to collect online data and use these online data to adjust our uncertainty sets. And we feed uncertainty sets into our algorithm that gives us control signals. So hopefully, as we collect more data, we will see our uncertainty shrink about the unknown of the system and find a good way of controlling the system. And so as I mentioned, right, for a lot of the systems that we consider in energy systems, transient period is important, where you have huge amount of uncertainties. There's just no way for you to make it small in a very fast time, in a very fast pace. And so it really matters how we can perform sample efficient uncertainty set learning. And even if you can make these uncertainty learning algorithms really, really efficient, there's a limit to it. And in the beginning of this algorithm, you will still have to deal with really large uncertainty. And so we're going to address this by combining online learning techniques with robust control as a combination so that we can actually give it guarantees even when we have very little idea about the entire system. Okay, so for this talk, I'm going to describe 3 aspects of this framework that I think is interesting. The first is fast stochastic model adaptation. So we ask ourselves, right, if the noise or the system behavior or the disturbances are very benign and they're just noise, can we at least get some good convergence and fast convergence out of our algorithm? And the answer is yes. And the second part, I'm going to talk about how we build our control algorithms on top of these uncertainty sets. So in control, we know how to build control algorithms based on a particular model. But what if I give you a whole set of models? What can you do and still guarantee stability when the set is huge? Oh no, what did I do? Okay. All right, and finally, there's always going to be a theory and application gap. So I will discuss how these algorithmic ideas apply in practice with some high fidelity simulations in building control and power grid. Okay, so for the first part of this talk, I am going to introduce an algorithm that provides a fast learning rate that basically the size of your uncertainty set is going to shrink linearly with the number of samples that you get. And this is an upper bound that we get from this algorithm. But turns out that it also rate optimal in the sense that the minimax optimal rate you can get in the setting is also 1/t, which is the linear rate that we had in the algorithm. So our algorithm is actually optimal. So let's talk about uncertainty set estimation, right? This problem of estimating models and adjusting its uncertainty set using online data has been around for a long time. In the machine learning or data science community, this is usually referred to as confidence intervals. And here I'm listing a few canonical and popular methods that people are studying. And among them, I would argue the most popular by far, the method that people are using in combination of control theory is least square estimations because it's simple, it just works no matter what your modeling is. You can always compute the least square estimation solution, and it works well in practice. But instead of talking about least square estimations, I'm actually going to talk about this other estimation method called set membership estimation, or SME for short. So this is a traditionally control theory tool. People have been using it to do state estimation, and it's been around for a long time. And the reason we got interested in this method is because because it performs really well. Okay, so on the left-hand side, the first plot, I'm plotting like the uncertainty set diameter trajectories over time as we collect more data. And so the blue line is least square, and the yellow line is set membership. So not only is set membership orders of magnitude smaller in terms of the size of its uncertainty, it also kind of looks like it's converging faster. And on the right-hand side, I'm presenting kind of the visualization of the two uncertainty sets. So obviously, you want to work with the much smaller yellow region than the blue region. Okay, so what is set membership estimation, and what is the thing that we're trying to estimate here? We're going to consider a linear dynamical system here, where the system dynamics is parameterized by matrix A and B, and we will assume A and B is entirely unknown to us. And furthermore, we will assume that our disturbances are IID, so benign, but it has a bound, capital W, on it. And so the set membership estimation algorithm goes as follows. At every time step, t, I'm going to look at the entire trajectory that I've seen so far from k equal to 0 all the way to t minus 1, and then find the set of models that are feasible with respect to this trajectory, right? So I know that the disturbances are bounded, they're not just like infinite. So there's got to be a set of models, feasible models that can generate this particular trajectory that I see. And there are models that are just infeasible. It's implausible for them to beat our true model. So it's as simple as that. And if I visualize this, let's say we start with some arbitrary, I'm showing this as bounded, but you don't have to start with any bounded or even anything. But let's say we start with a P0. Every time step, as I collect one transition data from K to K plus 1, I'm actually going to get an intersection of two half spaces, right? Because we have H infinity, we have infinity norm, and so these are linear constraints on our A and B. And I get a smaller set, hopefully, and I will observe a new data, and the set will hopefully shrink. Okay. So of course, I'm visualizing them to be shrinking. Do they actually shrink? And under what condition do they shrink? This has been studied in control a lot since the 90s. So we do know set membership estimation algorithms can converge in a lot of regular settings, and variations of set membership estimation has also been studied. They all converge. They're great. But nobody has answered how fast they converge, right? And that's what matters to us when we're trying to deal with an emergency situation, when the grid topology changes and we just want to stabilize as soon as possible. So that's what we want to do here. And with this, we just analyze this naive vanilla set membership estimation algorithm. And our guarantee is that turns out under some technical assumptions with high probability, the membership sets, so uncertainty sets, the diameter of those are going to shrink linearly with the number of samples. So it's a dynamical system. We get one transition data per time. And so up to time t, our diameter of the uncertainty is just going to shrink like 1 over t. Okay, so this is great because compared to the state of art, where a lot of papers are using least square estimations, whoops, I had a big major I edited this last night, and I think I accidentally made something wrong. It should be square root t. Apologize for the actually important typo. So least square estimations are 1 over square root t, and so compared to 1 over t, square root t is much slower behavior, and so this would also validate what we observe in practice, which is that we get smaller sets and we get faster convergence. Now, what am I hiding under the rug, right? As a theorist, we should always ask, what are the assumptions? So for the technical assumptions we're making, there are two major ones. And the first is that we're going to assume that these disturbances are not only IID and bounded, but these disturbances must visit the epsilon neighborhood of the boundaries with probabilities that scale linearly with the epsilon. And so let me illustrate this. Let's say we have a scalar disturbance W bounded between negative W and positive W. So denote the epsilon region here. And so this assumption just says that your disturbance WT at every time step T has to visit these yellow shaded epsilon region with probability that is at least linear in epsilon. And this holds for all epsilon. Okay. And so an example of this is a uniform distribution, right? You get uniform distribution, then the probability of visiting epsilon away from the boundary is epsilon over 2W. Now, the second assumption we have is relating to excitation. So we want, with at least some probability, the smallest singular value of our data covariance is bounded away from 0. And this, in control terms, just implies that we have persistent excitation with high probability. And this is a clear distinction from usual system identification papers, which require you to be deterministically persistent exciting. For a system like this, it's much easier to ensure high probability persistent excitation than deterministic ones, especially think when you have small data, right? All right, so with these assumptions, this is the rate that we get compared to now the correct least square estimation rate of 1 over square root t. There's another thing I haven't talked about, and you should probably ask too. I talked about the square root t and t. I didn't talk about an x, which is the size of your dimension, right? We have a much worse size dependencies. Our polynomial looks pretty bad. But we do believe it could be a artifact of our analysis, because when we run this in simulation for the uniform distribution and also truncated Gaussian distribution, we see that the scaling with dimension is very similar to the least square estimation. So if we, put this algorithm against least square on a less idealized, but still pretty much toy example of a linearized flight control, you will see this really nice, faster convergence behavior of the unknown model uncertainty set learning. Okay, that's great, but there's one last thing that I didn't tell you, and I'm hiding under the rug. This entire algorithm and analysis require us to know exactly what the bound on the disturbances is, right? And in fact, the assumption is very much leveraging on visiting the exact boundary of this of the disturbance bound. So what if we do not know the bound on W, right? Can we still run the same algorithm? Let's just say we have conservative estimation of W. So even though the true system is bounded between negative and positive W, we're going to plug in 2W into our set membership estimation algorithm. How does that look? Okay, so this orange yellowish line is the W being tight. So if we just use two times the bound, the performance immediately deteriorates pretty badly. And if we use 3, 5, 10 times the actual bound, it just looks really bad. Okay, so this is not yet a good algorithm for us to convince ourselves that that's what we should use, because in reality, we almost never know the exact bound. Right? Okay, so towards this, we came up with an upper confidence bound version of set membership estimation. And so the algorithm goes like this. We're going to now denote a set p hat t as opposed to pt, where this p hat t is parameterized by the assumed bound on disturbance, which we call eta. And so we are going to compute lower bound on what the true disturbance bound W can be. And to compute this, we find the minimum amount of disturbance you need, eta, in order to generate the system behavior you have seen so far, right? So any value below this eta, or below this W bar T, your trajectory, you won't see this trajectory, right? Okay, so our key insight is that this optimization as is currently being presented is not like a mathematical or tractable way of solving it, but you can equivalently write it as this minimax problem. And the inner optimization function, where we're mapping A and B into this maximum value, is a convex function and monotonically increasing over T. So what this really is saying is that if we focus on this minimax reformulation, this optimal value coming out of it, the W bar T, is only going to increase over time, right? And so you would hope that this lower bound is going to slowly approaching your actual upper bound. And indeed, under the two assumptions we had from the previous theorem, the gap between our lower bound and this true bound is going to shrink also linearly with the number of data we get. Now, you can't use a lower bound in your algorithm plugging into p hat, because if it's a lower bound, there's no guarantee that your true system is actually lying inside of this uncertainty set, right? What you need is an upper bound. And so our idea is simple. We're going to add this gap, delta t, into the lower bound and choose that as our upper bound estimation for the actual bound into p hat t. And this is how we're getting an upper confidence bound SME set. And with high probability, the true system is going to lie in this set. So our guarantee is going to be very similar because of the approaching of the lower bound towards the actual bound is also 1 over t. So you basically get the same guarantee as if you know the true bound with some, I'm using big O here, so you can imagine the constants are a little bit worse. How does it actually look in terms of the simulation? So this is kind of the sad picture we had, right, with loose bound. And so if you run the set membership estimation algorithm with UCB, you will see that the convergence rate is matching. And even though we started with a bigger set, it very quickly becomes much better than least square and all the other loose bounds. Okay. And I'm not going to talk about lower bounds here, but turns out that this algorithm is rate optimal. 1 over t is the best you can get. And so that concludes the first part of my talk. I will pause here for any questions. All right. So now we have a way to, compute and adjust our uncertainty sets online when we have stochastic benign disturbances. What happens if the disturbances are just bounded but arbitrary, right? Can we still come up with some uncertainty set estimation method and build control algorithms on top of these on top of these uncertainty sets? And this is going to be a talk based on these two works, where I will briefly discuss communication constraints for network systems and time varying systems, which I believe are two very important aspects of applications, especially in power grid. Now, instead of going through each of these papers and give you algorithms, I'm going to abstract away the key ideas underlying both of these papers. Okay, so let's start with a simple centralized time invariant model just to get the key ideas across. Again, A and B are going to be assumed unknown here. And now our assumption of the disturbances is that it's just bounded, but it can also be arbitrary and potentially adversarial. So it's different from IID as before. And the second assumption we have is that the system AB is unknown and that it belongs to a compact convex controllable set. So with this in mind, we ask ourselves, why do we care if it's, adversarial or arbitrary? We can do the same algorithm, just try and come up with uncertainty sets and try to hope that it converges and, build control on this convergent point, right? So turns out that because we are in the adversarial setting or arbitrary disturbance setting, it can make learning or exploration really difficult. And here's a almost contrived example, but hopefully illustrate the main idea. So let's consider a scalar dynamical system where the only unknown is A star, that's our model. And A star belongs to this big interval of -10 and +10. Was there a question? Okay, yeah, so A star belongs to -10 and +10. And it's obvious there doesn't exist a single stabilizing controller that stabilizes everything in this whole region, right? So you must find a way to shrink your uncertainty. WT is bounded by eta. And our goal here is to drive the system into this region bounded between -eta and +eta. Now, if we know what A star is perfectly, we will choose U to cancel the dynamics exactly, right? And so we end up, if we plug this UT into the system, what we end up left with is xt plus 1 is exactly equal to WT. And this actually achieves what we want. But if we do not know A star, and if we want to use the technique I talked about in the first part of the talk, we want to use data to estimate A star and adjust it online, and then hopefully it will give us a good control policy. But it turns out that WT can just make you learn nothing about A star at all time if eta is large enough, just by canceling whatever you do, right? So if you're plugging this WT into the system, you observe X is at origin the entire time, no matter what you do. And so what this is telling us is that, there's a really bad news about learning or exploration. When you have arbitrary or adversarial disturbances, the state observation where you're always at 0, no matter what you input into the system, is just hopeless for you to try to learn anything useful out of the system. But if you take a step back, right? And some of you probably already noticed, the good news about control, which is what we really end up caring about, is that we do not care if we don't learn. In this particular case, adversary is helping us exactly achieving our goal of stabilizing in this small region around the origin, right? So this is kind of the underlying principle that we want to do when we're designing a control algorithm, where we want to force any potential adversary or the arbitrary disturbance to either hide information from us, but it has to help with our stabilization goal, or it can try to make us unstable, but it must reveal information about the uncertainty. So one of the two. And this is in direct contrast against the idea where we could take the first part of the talk and try to inject huge input into the system and try to overpower the adversary in order to get useful information out of it and try to give convergence guarantees about learning. Again, we care about control here. We don't care about learning. And so this really is a general online exploration and exploitation strategy, and it's been around for a long time. So even in the control community, there is this whole literature on dual and adaptive control where people try to do this in a very smart way. But unfortunately, even though we have a lot of stability guarantees, I don't think the type of adversarial disturbances that we're talking about here has been addressed in the literature. And in the online learning community, they're very familiar with the type of adversarial model that we're talking about here. But a lot of them don't care about stability. They start with a stable system. They assume that disturbances cannot make you unstable. And so they can have really great regret, fast convergence, but no stability. And so hopefully we can combine these two communities and get both stability guarantees for a variety of systems that we care about, and while doing so, while we're going against adversary. So the high-level idea of this whole algorithm is just to stick with the hypothesis model until proven wrong, because anyways, you're likely to not get something useful from your data. And we're hoping that when the model is proven wrong by the data, we will probably see an unstable transition, but we'll gain information. But when the model is not proven wrong, which means we're not getting useful information, we're hoping that our controller is actually stabilizing our system. Okay, that's what we're going to do to realize kind of the intuition above. So what is this algorithm? I pretty much tell you like the big bare bone of what this algorithm is going to go. So let's say, again, we're starting with an uncertainty set P0, and our true model lies somewhere there. And every time step, we'll observe the transition from the previous state xt minus 1 to xt. Okay, and then based on this transition data, we're actually going to stick with set membership estimation, right? It doesn't matter if it's IID or not. As long as our disturbances are bounded, we can generate this set of models that are consistent with everything we've been observing, right? And based on this set, we're just going to pick a model out of this set. And this model that we pick can be very much wrong and very far away from the true model. We have no guarantee about it. And based on this picked model, we're going to design controller based on it to stabilize it. And this part, we can use any existing control literature, right? Because we already have a model, hypothesis model. And so once I generate a UT, I input this back into the system and the state transition and gives me a new data. And so if you would, already see, right, the way I pick this hypothesis model is actually deciding how I'm exploring the system, because it's generating a control action that tells me what the next transition is. And so it's very important how we pick this hypothesis model. Now, if this algorithm continues, we're going to observe a new data that carves out some new plausible models for us. And in this case, our previously selected model is proven wrong, right? It just cannot be a plausible model. So we shrink the set, and we're just going to move to a new point in the new set, and we'll continue this process. As simple as that. The only other option that we will have, scenario we'll have, is that the new data we get is not as informative as we would like it to be. So the set hasn't shrunk enough for us to invalidate the previous model. We'll just continue with the same model, okay? So how do we actually pick these hypothesis models for us to drive the behavior of making the set shrink or not shrink? Now, in the first scenario, when the hypothesis model is invalidated, so the set is shrinking, obviously, we are gaining information because the set has shrunk enough for us to pick this model. But our control action is actually going to be bad. It's because we have just used a model that is being proven to be wrong to generate a control action for the true system, right? Now, if we're in the second scenario where our hypothesis model is remaining in the new set, then likely we have not gained much information, but our control is actually going to perform well. And that is kind of the key and subtle point of this whole algorithm. And to kind of explain this in a simple example, let's consider X transition from X1 to X2. And we know we have injected U1 that stabilizes this hypothesis model, theta hat 1, which could be wrong. But because theta 1 after observing X2 remained consistent, or instead of the set after observing X2, we can treat this data as if it had been generated by this hypothesis model, right? It might as well. And if you just focus on this scenario or this imaginary scenario where X2 is generated by this hypothesis model, and focus on the dynamics, you will see that we have the model A hat 1, B hat 1, which is theta hat 1, and we use the U1 that stabilizes this model, right? So this one-step transition must appear to be stable because our model is not invalidated. Okay, so to summarize, every time our selected model is invalidated, we gain information, but our control is mostly going to be bad. But every time our selected model remains consistent, we may or may not gain a lot of information, but our control is guaranteed to be stabilizing this one-step transition. And recall the contrived example, right? What we care about really is the control behavior, not learning about what the true model is. And so we're going to focus on control. We're going to try to design algorithm and select model in such a way that we get as much of these thumbs up control scenarios as possible. And this is especially useful, again, in low data kind of transient behavior regime, right? When you really cannot have a small uncertainty. And so this is what we can do. So what are we going to do? We're going to select models that remain inside of the future consistent set as much as possible. And I call this behavior consistency. And we don't know what's going to happen in the future, but we can try. So the more consistent our model selection is, the less bad control behavior we're going to generate. And to quantify what I mean by a consistent model selection, let's use a notion called total movement of the hypothesis model, which is just the sum of the distance that you have to move between model selection every time you're invalidated, right? You only move when you're invalidated. So we're counting how far you've been moving. And this notion isn't, the first to be used in control algorithms. There's a collaborator of mine who used this in the previous work for nonlinear robotic systems. And here, smaller delta t is less bad control action. So how do we select hypothesis model that actually minimizes quantity? Turns out that there's a long line of work in online learning community that studies this problem of selecting a point out of a set that's convex. And the idea is that you want to select points into sequentially revealed convex sets such that you minimize the total distance. And this very much fits our idea of what we want to do. And there are a lot of algorithms for this, and most of them follow the principle of just trying to select models deep inside of the set, right? So if you are invalidated, you must have almost in a way cut this model by half. So, in terms of the worst case movement guarantee, no matter what the adversary is doing, no matter what kind of convex sequential body you're given, we can still have delta t being bounded for all t as t goes to infinity. And that's what convex body chasing algorithm can give us. So we're going to now, in our algorithm, choose hypothesis models using convex body chasing. And so our key insight here is to connect this total movement with the closed loop stability. I won't go into detail, but I will tell you what the result looks like. So just a reminder, this is our algorithm. Now we're going to plug in whatever convenient convex body chasing algorithms we want into this part. And then whenever we come up with a model, we'll just use any model-based controller depending on the scenario. If I have network systems, I'm going to use distributed controller that can handle delay, communication, like localization. If I have a system with constraints like actuator saturations and state constraints, I'll use model predictive controller. If I have just a time varying systems, I can use something that has natural robustness building like LQR in state feedback. So here are the suite of results. Most of them looks like the following, where we will have something that looks like the input to state stability result. And so the most important thing here to note is that there's this constant C, right? And this constant C actually depends exponentially on the worst case system theoretical constants in my entire set. So it could be really large. And we get exponential convergence. And the total size of my state over the entire trajectory will, of course, depend on the worst case disturbance, so W. Now, if we move on to the network system case, we will have a very similar result if I just plug in a distributed controller into my algorithm. But now this constant, instead of depending on the global system dimension, which could be really horrible for large scale network systems, it now can just depend only on the maximum delay in a local neighborhood if you have communication delay, and it will just depend on the size and size of the local neighborhood in your distributed control design. Okay, so there are distributed control algorithms that make your controller scalable and compartmentalize your network into smaller neighborhoods. And finally, for LTV systems with a very similar idea, slight change, we can get similar results where now it depends on the exponential decay factor from the LQR controller that we plug into our algorithm. And the stability will depend exponentially on how fast and how much your actual model is moving, which is consistent with what we know about linear time varying systems. If they're moving a whole lot, there's not very much you can do in terms of stabilizing them. Okay, so that concludes the second part of my talk, right? We talked about an algorithm that builds on top of these set membership uncertainty sets, and we talk about what is an algorithmic idea to stabilize the system despite knowing very little about the system. If there's any questions, I'll take them now. All right, and on to exciting plottings, right? The application. So as I just presented to you, everything depends exponentially on everything else, all right? So it could really be horrible. And that's what I call, right, the theory application gap, theory practice gap. So luckily for us, even if the theoretical guarantees are worst case and therefore we're stuck with these exponential dependencies, the actual application of these algorithmic ideas in practice, at least in high fidelity simulators, end up performing really well. So we're going to see an example of this. So the algorithm has been applied to power systems and building control, HVAC control, but I'm only going to talk about the building control system here. So as a primer, buildings are a major driver for global energy use and emission. It accounts for 30% of the entire consumption and also a similar amount for the carbon emission. And among the entire building systems, the HVAC, which is the part that controls the AC and the heating of the building, is responsible for a huge, significant portion of the system energy consumption. But the hard part about controlling these systems is that buildings are really complex. You look around the campus, there's not going to be a single building that looks exactly the same, right? And so that means that their HVAC configuration is also different. Their water and air systems are different. There's complex thermodynamics you have to analyze. So it's very hard and expensive to learn a model every time you want to control a new building. And so people have come up with ways to do transfer learning for HVAC systems. One thing I did not mention is that these HVAC systems, they're highly nonlinear because they're thermodynamics, and there are a lot of unknowns about them. So like learning is kind of like a natural idea of coming up with ways to make them energy efficient. But you want to transfer it between different buildings because they're all very different. Now, the upshot is, of course, if we successfully do this, we can adapt from previous control strategy we learned, training with lots of data, to a new building very quickly, and it can reduce energy very, very significantly. But to do so, as is with almost all reinforcement learning and transfer learning, no matter how good the regret looks, eventually you still have to use a very large amount of data, in particular representative data, for this new system that you're trying to control. And so that's one thing, but I think what we could care about more is that it's hard to enforce constraints when you're transferring even a constrained reinforcement learning that satisfies some constraints into a new building with a whole new set of constraints, right? So if you've ever sit in a room during summer that is way too overheated or way too cold, this is what we want to guarantee, right? Okay, so I'm going to talk about, in particular, the thermal comfort constraints in a building. So here I'm plotting a 24-hour trajectory of the temperature from some stock building in the DOE software. And the purple and yellow line are the average temperature profile averaging over multiple days. And the dashed black lines are our thermal comfort constraints. And the red shaded region is constraint violation. So every time, every 15-minute window, you get a constraint violation, you have a shade of red. So the more red, the worse. And this is two benchmarks, algorithms that are well established in the community. Now, we come up with an algorithm called OCFT, which is this green line, that is able to significantly reduce constraint violation just by visualization, right? So how do we do this? Instead of, again, going through the algorithm, it's building on very, very similar ideas. And so this is a block diagram. I'm a control theorist. I love block diagrams. So you have a stock building. You have these inputs into the system with different kinds of disturbances and exogenous inputs. And you see the state. And the state gets passed through some existing RL policies you're trying to transfer into the new system. And instead of directly using it, we're going to pass it through a safety filter called OCFT that gives you actions that are trying to conform to the constraints in the new building. And in particular, inside of this OCFT is, no surprise, a convex body chasing algorithm that tries to adapt the nonlinear model of the new building. It tries to learn the nonlinear model of the new building very quickly, and then, goes through some optimization to try to ensure safety and constraint violation isn't happening. All right. So let's jump straight to the experimental result. This is OCFT, our algorithm, comparing to 4 other transfer learning and the benchmarks. And this is a simulation that is done on Energy Plus, which is provided by Department of Energy. It's a high fidelity simulators. And we simulated this across 19 US climate zones, so all type of climates. And we see that on average, our algorithm reduces constraint violation by 81%. So that's a big win. And it only uses 11% more energy on average. And, in theory, it is hard to, I can talk all about least square is, not the right thing to do. And the set membership is what you should use because it has faster convergence rate. How does it actually translate into practice when really we don't have IID? We also don't have a true bound. A lot of assumptions are just breaking, right? So we try to do this, test this in this simulation where we run our exact algorithm that is building on convex body chasing and model adaptation and robust control. With, we just replace the component where it's convex body chasing, we replace it with least square. How much does it actually change? So here we're plotting the 19 climate zones, and these numbers around the circle is each zone. And the closer you are to the diameter of the circle, the more violation you're making. So just by swapping this one component of an adaptation submodule, we get so much worse violations, right? So convex body chasing, this whole idea of, in a way, worst case, trying to compete against what the adversary can try to harm you is really helpful here. And with that, I conclude my talk. Thank you for your attention, and I'll take any questions now.
Thank you so much. Yeah, are there any questions in the room? And I'll also monitor on Zoom as well.
Yes.
So going back to the first part of your talk,
Okay.
the learning rate, I wanted to make sure I understood it because when we looked at some of the plots of learning rate, the uncertainty versus T, I guess that doesn't look obviously linear in T to me. And I was wondering if there's hidden things happening like dimension changing.
So are you saying the plot doesn't look linear? Yeah, it's algorithm.
Oh.
Yeah, sorry, maybe it's not. I probably should have mentioned this. Yeah, it's logarithm, so that's linear.
Easy answer.
Called linear convergence though, because you multiply the error.
Yeah, in like optimization as well. I think
Yeah.
even though something's exponential, you call it linear because you take the logarithm of that and that's linear.
Right.
Yeah. Thanks for the clarification question. I'm glad you asked.
I have, oh, sorry.
Oh, I've got one. So at least squares algorithms are often very efficient to optimize. And if you're doing this sort of convex chasing and you're chopping off parts of your domain, then you have to use, convex algorithms then to solve that. So even if you converge faster, is each stage of your solve then more expensive?
Very good question. That's, I guess, another catch of this type of algorithm. So the naive algorithm I'm introducing here, as just show this algorithm real quick. So on the top, right? So you get a linear constraint every time step you get a new data. And so this constraint, technically speaking, would just grow into infinity. So that's really bad. But there are a lot of recursive ways of dealing with it. I mean, I would argue the same thing for least square, right? If you don't do recursive least square, your minimization problem also grows to infinity as you get more data. So it's very similar. Now, how do you generate convex body chasing? Algorithms where you can generate a data, a point out of a set. There are a lot of algorithms out there. So if they trade off efficiency with performance in terms of guarantee. So the efficient ones use linear programs. randomized linear programs. So it is efficient in that sense.
I have I guess a question on how difficult it is to generalize this beyond like a linear dynamics model to something like a linear model in terms of your like unknowns, but perhaps the nonlinear features, right?
Yeah, that's a
Yeah,
good
it
question.
feels like it would generalize like pretty naturally, but maybe there's like some nasty stuff.
It does. So if your nonlinear basis functions are analytic,
Yeah,
you get very much the same convergence rate.
okay.
There's a follow-up work very recently by a collaborator. And the last part of my talk where I'm talking about building control and we're adapting these models for buildings, these are feature functions that we learned using reinforcement learning too. So these are like input to convex neural networks that we're using to adapt using convex body chasing.
Oh, very cool. Yeah. So for I mean, I can look at the recent work, but for the bounds that we had here, like you had the state dimension showing up for the extension to the basis functions. Is that based off of the number of basis functions that you have, or still like the dimension, the true dimensionality of the dynamics?
I don't remember.
Okay, yeah, I can read the paper.
But I do think it's the number of bases.
Okay, great. Anything else in the room, or I'm still monitoring Zoom? Right, well, let's thank our speaker one more time.
Thank you.